Today we will study motor effect, generator and transformer. Motor effect is related to the force of a magnetic field on a current carrying wire. What generator and transformer are related to our lecture on electromagnetic induction. So let's start with DC motor effect. To understand DC motor effect, let's first understand this a very simple picture of a DC motor, that where we do have a permanent magnet where we have the north pole toward the left and the south pole toward the right. So this means that the direction of magnetic flux density is from left to right along this blue vector. And then we consider that we do have a single turn rectangular coil which is inside this uniform constant magnetic field. So we need to actually also be careful to understand the configuration of the connection of this rectangular coil with our DC battery, where we do have a negative electrode over here and a positive electrode here. So this means the current is flowing from positive to negative along this direction. So here this battery is connected through a connecting brushes with a semicircular copper or brass connector. So if you look carefully, then you can see that these are two separate connectors. One is connected with the positive terminal and the other is connected with the negative terminal of the battery. So if, for example, you look from this side, then you can see that it will be actually just like this, meaning that they are actually the semicircular connectors. So here we do have these connected brushes that are going to the battery. So here what happened, that these connectors actually they are keeping their polarity. What when this coil will turn, then the polarity will change of the coil. How and why, that what we will understand now. So now what is happening here, that the current is flowing along this direction. This is actually, you can see that this is a counterclockwise direction of the current. Now, if we consider that this AB side, in this AB side, the current is along this, which is perpendicular to the magnetic flux density. Now you can use your left hand rule to understand the direction of the force of this constant uniform magnetic field on the right side of this rectangular coil. So the first finger is towards right, the second finger towards the screen, and then you will find the thumb is downward. So it means that on the right side of this coil, the force of the magnetic field is downwards. Now we can see the force on the left side of this coil. On the left side of this coil, that's we can say, for example, this is a CD. Now you can use again your left hand rule, and this time the first finger is again towards right, but the second finger towards you. Then you can see that the force on this side is upwards, which is F. And this F, the force of the magnetic field, we know it is equal to the charge, or you can say in terms of the current, that is equal to the magnetic flux density, the current value, and the length of the wire inside the magnetic field. And here we also know that if there is an angle between the current and the magnetic flux density, then we will have a sin theta over here. So this is the reason that on these sides, we would have actually the zero angle here are 180 degrees. So it means that our this term sin theta term will be zero. So there will be no force. So then in the result of the force on the right side and the left side, this coil will rotate clockwise like this over here. What would happen, because we have a DC connection, DC battery connected with this coil. So what will happen when this coil, it turns 90 degrees, and then it is over here, meaning that now it is a vertical coil. So then in this case, our configuration of this rectangular coil will be like somewhat like this one. Now, this coil, when it will have this side, which we actually said that it is CD, so the force is upwards. And then on this AB side, the force was downwards. If the force will remain like that, then you can see that at this position, the forces are cancelling the effect of each other, then coil should not move ahead. So now what will happen, that if for an example that we change the polarity of the current, meaning that the current first it was going along this direction, now if we rotate other way around, then what will happen, that the direction of the force will change. So here it will go up and here it will go down. So now you can see that what is happening, that this coil, this side of the coil, the upper side, it will be pushed down and upper one will be up, and this coil will continue to rotate clockwise. And how we can change the polarity? That actually comes here from these brushes. So what happens, that this side, for example, is connected over here, other side of the coil is connected to the other side of this, you can say, the semicircular structure. So now when it will be rotating clockwise, then at the end, this is connected over here and other side connected here with a very little move. So now you will flip your right side to the negative terminal and left side to the positive terminal. So with this jump from one side of the connection to the other, your actually this coil is changing its polarity. So this is the reason that our motor will continue in a one direction of the rotation. For example, in this figure, it is a clockwise direction. So now we understand that what we actually need in a DC motor, that we need the coils and then we also need to change the polarity of the coil with every half cycle. So that is why we have this semicircular structure over here, and there is the gap in between, and the wire is actually slipping inside these actually copper connectors. So then you can see here, this is our connection. This picture actually shows here the actual structure of a DC motor, where we have a permanent magnet, we have a coils, and these are the connections. And here we have, this is connected, connecting brushes, so whatever you want to call it. So then in this way, the DC motor works. Now, the most important part is the AC generator. So how the AC generator works, let's go to understand this. So here, AC generator is an opposite effect to the DC motor. So in DC motor, we provide current and the coil rotates inside the magnetic field. But in case of AC generator, we mechanically rotates the coil inside a uniform magnetic field that induces EMF in the coil. So how does it happen? So this is a very simple simulation where you can see that we do have a north pole and south pole of a permanent magnet. So between these two poles of the magnet, we do have a uniform magnetic flux density B. Now, we have this coil, and note here that this coil, this time, each terminal of the coil is connected to a separate ring. And this ring is a complete cycle, so there is no gap as we had in case of DC motor. And then we have connected it with here, for example, ammeter that is actually giving us a multimeter, you can say, which is giving us the readings of the induced EMF. So, how this works? We learned about previously about magnetic flux phi, which is equal to the magnetic flux density times A and times cos of theta. So this theta is the angle between the magnetic flux density and the cross-sectional area of the coil. So if, for example, we consider that we have again here a rectangular coil just for simplicity like this, then here this is the cross-sectional area of our rectangular coil. And we also know the Faraday's law, which actually gives us the value of induced EMF is equal to negative sign of number of turns and first order time derivative of magnetic flux. So if we use this formula of magnetic flux, then we can find that it is equal to N and the time derivative of B times A into cos of theta. So here, just to remember that what this theta is, actually, because this is rotation, so rotation of the coil. So this actually, the theta is our angular displacement. This is angular displacement. So this angular displacement can be equal to theta is equal to omega t, where omega is angular velocity or angular frequency. So if we connect these all the things here, then we can very easily find that we have N. A is a cross-sectional area which is constant, so it is outside this derivative. And now we have a magnetic flux density because of the permanent magnet. This is also constant. And now you can see that only time dependent variable is that is the sin omega t. And the time derivative of sin omega t is cos omega t and times omega. So minus omega, which is the angular velocity, n number of turns, a is cross-sectional area of the coil, and b is magnetic flux density, and times, sorry, this is here we must have a cos. We then going to apply this time derivative, then we will get the sin omega t. Okay, the derivative of cos is a negative sin, so we will get here positive sign like this. Okay, good. So now we understood that what will be happening here, that when this coil will be moving inside this uniform magnetic field, the flux crossing this cross-sectional area of the coil is in fact changing as a function of time, because this coil is continuously moving, and this theta is angular displacement, which is equal to omega t. So this flux is time dependent, the flux which is linked with this coil. Now, what will be the result of this rotation and how we will get the induced EMF? The induced EMF will look like this. And here, you can see that our induced EMF is 0. So, okay. So now we understand that how the induced EMF will look like in the AC generator. So the formula that we just derived, we can write it in a very simplified form, that the induced EMF must be equal to some constant. Let's say this is A prime. So A prime means that it is not a cross-sectional area of the coil, and times sin omega t. Omega is angular frequency, t is the time. So now we can see the different situations. So for example, we are at time t is equal to 0, and our situation is that we have our coil and this coil is just, actually you can say, in this condition is a vertical to the magnetic flux density lines. Then for example, you can see magnetic flux density is like this B. What the cross sectional area, the vector of the cross sectional area is along the normal of this coil, it is like this. So it means that the angle is 180 degrees. Now, if this coil is going to rotate like this clockwise, then it means the angle is actually going from 180 degree towards 0 degree. So it means that this rotation, it is actually in the second and the first quadrant of a trigonometric angle. So now here, what will happen, that when you are going to change it, then the flux linked with this coil will be decreasing. So it means that as a function of time, your flux linked with the coil is changing, and you are going to get some induced EMF, and that will be positive. And now it is actually going to increase up to you are in this situation where the angle is 90 degree between your this the area of the coil and your this magnetic flux density. So in this situation, what will happen, that there is no any more rate of change of the linked magnetic flux. So there is no even linked magnetic flux. So in this situation, what is happening, that the induced EMF, which is at the top here, it will be now starting to decrease with the further increase sorry, with a further decrease of the angle, because I'm actually considering here that it is 180 degrees and here it is a 90 degrees. So then now it will be again moving ahead toward the 0. What the magnetic flux will start to link with the coil. So now it means that your flux is increasing as a function of time. What your actually this induced EMF is decreasing toward the 0 when you will have this situation over here. So in the 90 degree we are max because we have sin dependence. So now at this situation, when we have a 90 degrees more, then our magnetic flux density is over here and area is actually also over here. So both are parallel and angle is 0 and we are here at 0. And when we will move 90 degrees more, so now our area is over here and B is over here. And you can see that actually this is the situation of 270 degrees. So we will be at max, what, with negative sign. And then again, we will come back to our the initial situation, meaning that we have completed our one cycle. So this is the situation that I will call it that it is a 180 degree situation, which is the first point over here. And our actually induced EMF, it came back to 0. So once again, have a very quick look, because this is very, very important. If you understand this, then you can understand that how generator works and why it is always the AC generator. So here what is happening that we have our coil where the cross-sectional area and the B magnetic flux density, they are at 180 degrees to each other, and the sin 180 is 0. Now actually you move toward the 90 degree. That means that our linked flux with this coil is decreasing. That means that there is induction, and that induction is positive, and it is going up sinusoidally to the max value at 90 degree. So then you actually move ahead, you reduce your angle from 90 degree toward the 0 when the cross sectional area and your magnetic flux density are parallel. Then you will get the 0 situation. So when I say that the area and magnetic flux density parallel, that means actually the normal vector of a surface area. Now, if you will go 90 degrees more, then it means we are in this situation. So our angle is actually what? 270 degrees, and sin 270 degrees is negative max over here, -1. So we will get the maximum induction, what? Negative. Then again we move 90 degrees more, and that means we are in our first situation and we are back. So we have a sinusoidal induction of induced EMF. So induced EMF is always alternating. So it is changing its polarity. So hope you understand that how AC generator works. With this understanding, let's also try to understand the working principle of a transformer. Okay, let's start understanding the working principle of a transformer. What a transformer is. A transformer steps up or steps down alternating voltage. How it works, let's understand its working principle. So in this diagram, I show you a very simple configuration of a transformer. Here in the gray material, it is a soft iron core, and this soft iron core is actually has a very special use, because this soft iron, its magnetic field, or you can say its ferromagnetism, we can very easily switch with externally applied magnetic field. And you will understand when we will discuss in details that why we need the soft magnetics or soft ferromagnetic materials to form the core of the transformer. And on this primary side, which is the left side of this transformer, we have a coil which is connected to our input. And this input is alternating. So we are actually giving alternating current to our input coil, which is the primary coil. And similarly, we are actually also getting the alternating output voltage, or you can say the alternating current at the output coil, which is our secondary coil. So what is happening at the primary coil? When we flow the current through this coil, we know that magnetic field will be generated because of the flow of the current inside this coil. And that will actually polarize, or you can say induces, the magnetic field inside this ferromagnetic core. So that will link with the secondary coil. Now, what is happening? That our current is alternating. It is going from 0 to max, back to 0, minimum, and then again 0. Similarly, magnetic field produced because of this, you can say the alternating current, we will have induced magnetic field, which will also be alternating. So this means that the flux inside the secondary coil, or in simple words, you can say the flux linkage to the secondary coil will be changing as a function of time, and we will have induced EMF in the secondary coil. So we will have some induced EMF. That means we will have output because of induction. So we can call it that this is Vs. The input voltage is the Vp, for example. The number of turns in the primary are the Np, number of turns in the secondary are Ns. So the working principle can be understood by transformer equation, which is Vp over Vs is equal to Np over Ns. Now, if our Vp is bigger than Vs, so it means we are reducing the voltage. So output is smaller. So it means that transformer is a step down transformer. It is a step down transformer because we are decreasing the voltage. So if Vp is greater than Vs, it means Vp over Vs is greater than 1, and then similarly our ratio of number of terms of the primary to the secondary will also be greater than 1. It means we will have a more number of turns in the primary compared to the number of turns in secondary. Otherwise, if our Vp is smaller than the Vs, then we have a step up transformer. Step up transformer because we have increased the voltage at the output. For our these computer chargers or the mobile chargers, we use a step down transformer because we actually reduce our input voltage from 230 volts to approximately 20 volts. But when we transfer the power from the power generators to the grids, then we actually increase the voltage in thousands of the voltage where we have to use a step up transformer. So here you may ask a question that if we are, for example, particularly in case of the step-up transformer, we are increasing voltage from the lower value to the higher value, does it mean that we are actually generating additional power, meaning the additional energy? So then what will happen to the law of conservation of energy? In fact, the law of conservation energy holds. What does that mean? This means that the power at the primary coil and the power of the secondary coil must be equal to each other. According to the law of conservation of energy, then it means that we are considering that there are no losses. So then in this condition, we know the power is the product of the current and the voltage. So the current in the primary times the voltage in the primary is equal to the current in the secondary times the voltage in secondary. So now we can take this voltage on one side. So voltage in the primary divided by the voltage in secondary is equal to current in secondary divided by the current in primary. So now from this equation, we can very easily understand that, for example, if you are going to increase, if you are going to increase our secondary voltage, meaning that Vp is smaller than Vs. So this means that Is is smaller than Ip. If Vs is increasing, Is is decreasing. So this is the reason that our actually law of conservation of energy holds. If voltage is increasing, current is decreasing. As in my example of the transfer lines, that we increases the voltage. The main objective in increasing the voltage is to decrease the current, because by decreasing current, we can reduce a dissipation of the energy in the form of thermal energy. So now here I would give you an assignment that, for example, we have our input voltage of 230 volts. Now, what I want the output of 20 volts. Now you need to design a transformer with some number of the primary number of turns in the primary coil and number of turns in the secondary. So this is what you need to think yourself, and you need to design a transformer to charge your computer. Thank you very much for carefully listening and watching, and I hope you understand. If you do have any question, just leave it in comments section. Thank you very much. Bye bye.